And now let's consider the third case, the case of two numerical variables. I guess that this case is the most important one of the three cases we are discussing today. So this situation is subdivided into three subcases. The first one is when our two numerical variables are normally distributed. And so to understand what we are going to do, let me remind you the theorem I told you that if two random variables are normally distributed, then they are independent if and only if they are not correlated. So you know that in general, for all random variables, independence causes uncorrelation. So independence means that if two random variables are independent, they are not correlated, but not vice versa. So if two random variables are not correlated, this does not mean that they are independent. But there is an important particular case when absence of correlations causes independence. So when not only independence causes uncorrelation, but uncorrelation also causes independence, and this is the case of normally distributed random variables. So for normally distributed random variables, independence and absence of correlation, zero correlation, is the same. So this means that in this case we can test hypotheses not on independence but on zero correlation. And what we use to test this hypothesis is the sample correlation coefficient that can be found according to the formula, with the formula you see now. So you have two numerical variables, x and y. You have two samples, x1, xn and y1, yn. So for each observation you have two numerical values, xi and yi. And this is the formula for the sample correlation coefficient. So it also can take values from -1 to 1. So we have here the same situation as for the Spearman's law. So, but unlike the Spearman's law that shows us how strong the monotonic dependence is, sample correlation coefficient shows us how strong the linear dependence is. So linear dependence is a particular case of monotonic dependence. For example, y equal to x cubed. This function is monotonic but not linear. So the Spearman's coefficient shows us, so it can help us to find any kind of monotonic dependence, both linear and non-linear. So the sample correlation is only for linear dependencies, linear relationships. But so it can also take values from -1 to 1, and the situation is the same. So 1 means that there is a linear function, that y is a linear function of x, so increasing function. And -1 means that y is a linear function of x, and this function is a decreasing function, so the slope is negative. So then, after we have calculated the sample correlation, after we can, so when we have a sample correlation, we can estimate somehow how strong the dependence is, and then we can test a hypothesis. And so what we have here is very similar to what we have in previous case. So also there is a null hypothesis that sample correlation is 0. No, not sample, but just theoretical correlation. So Rxi here is correlation. Previously I used core symbol, CORR for correlation, but RXY is also used to denote the correlation. So the null hypothesis is that the correlation is 0, that in normal case, in case of normally distributed variables, means that they are independent. So, and as an alternative hypothesis, we can choose one of 3 hypotheses, either that correlation is not 0, or that it is positive, or that the correlation is negative. So, and this means a kind of linear relationship between x and y, a direct linear relationship, and an inverse linear relationship. Then, as for the test statistic can be of this test is calculated with the formula you see now, and it can be proved that if the null hypothesis is true, then the test statistic follows the student's distribution with n-2 degrees of freedom. So this means that the critical and acceptance regions are also, their configuration also depends on the alternative hypothesis in a standard way, and p-values can be found using the student's distribution function, the CDF of the student's distribution. So then, what we can do when our variables are not normally distributed, if we know that the distribution is not normal. So the second subcase is when the distribution is not normal, but we suspect that there is a monotonic dependence. So we have some reasons to think that if there is a relationship, if there is a dependence between x and y, this dependence it must be monotonic. So if it is so, then we can switch to the ordinal scale by ranking our observations and then apply the Spearman's test. So we have 2 samples, x1 xn and y1 yn, and we are ranking each of 2 samples. So we rank the first sample and we get R1, Rn, and then we rank the second sample and we get S1, Sn, and then we apply the Spearman's test. And so the third subcase is the situation when the distribution is not normal and we have no reasons to assume that, that a dependence is monotonic. So we suspect that there can be a non-monotonic dependence between x and y. What can be done in this case? In this case, we switch not to the ordinal but to the nominal scale by dividing both variables into several categories. For example, I told you that you can say you can divide height into three intervals, 3 categories, and you can divide weight in a similar manner, and so then you can fill the contingency table for these 2 variables. And after you have the contingency table, so then you can apply the Pearson's chi-square test, no association test, for nominal variables. So this is the standard approach we use for numerical variables. And now let me tell you a few words about what we have not discussed today. So you should know that there are several other methods for contingency tables, to analyze contingency tables, different from the Pearson's chi-square test and Pearson's coefficient. The most popular one is the Goodman and Kruskal's lambda. So this is a coefficient that shows how good the prediction of A when we know B and the prediction of B when we know A can be. And so there are also several other methods and several other coefficients for contingency tables that are used sometimes. You should know that there is another popular method for ordinal scale. So we have discussed only the Spearman's coefficient and Spearman's test, but there is also Kendall's coefficient and Kendall's test. So the coefficient is often called Kendall's tau, as it is denoted by the Greek letter tau. So, and I cannot say that the Spearman's test is better than the Kendall's tests anyhow, so they are both used both used very often. So as I'm limited in time, so I cannot give you both. And there are also other ways to analyze numerical data, so not only sample correlation is used, but there are also other approaches. So our today's lecture is just a brief digest of the most popular methods that are used to find dependencies in observations, to find dependencies between variables of different types. And now let us solve an example with the numerical data. For 10 years, the percentage change in Dow Jones Stock Exchange Index over the first 5 trading days of the year is given, and the percentage change over the whole year. So, and these changes are, so over the first 5 trading days, it was 0.5%, 0.2, minus 0.1, 2.8, 2.2, minus 1.6, minus 1.3, 5.6, minus 1.4, and plus 1.4. And over the whole year, it was respectively 14.9, minus 9.2, 19.6, to 20.3, minus 3.7, 27.7, 22.7, 2.3, 11.9, and 27.0. So the question is, can we say that there is a dependence? So if there is, it will be very interesting. It will mean that when we know the results of the first 5 trading days of the year, we can predict somehow. So we can predict the year as a whole. So let us assume first that these variables are normally distributed. So the first idea is to say, so let's assume the data be normally distributed. So in this case, we can say that we want to test a hypothesis of null correlation. So we can say that we want to test a null hypothesis that the correlation between x and y. So x is percentage change in the first 5 trading days, and y is percentage change over the year. So HO is that the correlation is 0, so that they are independent. And the alternative hypothesis is that the correlation, let us say that the correlation is not zero. Actually, we can suppose that maybe there is a positive correlation, so that if the beginning of the year was positive, then the whole year will be positive and vice versa. But so let us say that there is a correlation of some kind. So we need to find the sample correlation coefficient, rho hat. Rho hat. So actually, what we will need here, we need this big formula. So here there will be a sum for 1 from 1 to 10. And here we'll have xi minus x bar times yi minus y bar, and here square root of So let me not to waste our time by substituting the values and calculating all this here. So this is not a class on arithmetics. So let me just give you the answer. And the answer is that the sample correlation coefficient is equal to 0.369. I'm sorry, minus 0.369. So we expected positive correlation, but it is negative. Not so very high, not so very close to 1, more close to 0 than to 1, but than to minus 1, but still negative. Okay, let us now test the hypothesis. So if this, if it is enough to say that there is a negative correlation, this value, I mean this value of the sample correlation coefficient, is it enough to reject the null hypothesis in our case? So what is the formula of the test statistic here? So the test statistic equals r hat times square root of n minus 2 divided by 1 minus r hat so in our case that is minus 0.369 times square root of n is 10. We have 10 observations. So 10 minus 2 divided by 1 plus 0.369. And this equals to minus 0.8910. So this is the test statistic. Then we say that under null hypothesis, so if HO is true, then the test statistic follows the student's distribution with n minus 2 degrees of freedom. So that is in our case n minus 2, and that is 8 So we are to we construct critical regions. So as we have not equal sign here, we have two-tailed critical region. So two-tailed, here we have students quantile with 8 degrees of freedom of the level. So if alpha is 0.05 as usual, then here we have 0.025, and here we have 0.975, and so they are equal to 2.306 with plus and with minus, so 2.306 and minus 2.306, and we got minus 0.9892. Our T is minus 0.892. So the test statistic is in the acceptance region. So this is the critical region, this is the acceptance region, this is the critical region. So T belongs to the acceptance region, and this means that HO is accepted. So we fail to reject the null hypothesis. So the sample correlation coefficient is minus 369, but this is not enough to accept the alternative hypothesis, to say that there is a correlation. So why? The answer is the same as for the previous example. So because of the small sample, here we also have just 10 observations, and so just 10 observations, and that is why this sample is not enough. So we can say that it's better to take this data not for 10 years, but let's say for 20 years or for 30 years, so as these economical statistics are available for several decades, at least, of the recent past. So we can take more data, we can take the sample of the larger size, of the greater size. So if we do this, it will be better to analyze greater sample. And now, what about not assuming the normality of the data? So if we don't think that the distribution is normal, what can we do? So I told you that we can switch either to the ordinal or to the nominal scale. I won't solve the whole example for these two subcases, but let me just show you how this can be done. So the first idea, so if we think that the relationship is monotonic, we can just switch to the ordinal scale, and this can be done by ranking. So we rank the first sample and the second sample from the least to the greatest observation. So here I see that the least one is this one, minus 1.6. So its rank is 1. Then I see minus 1.4, rank 2. Minus 1.3, rank 3. Minus 0.1, rank 4. Then 0.2, rank 5. Then 1.4 rank 6, then 1.5 rank 7, then 2.2 rank 8, 2.8 rank 9, and 5.6 rank 10. Then the second sample. So the minimal observation is this one, minus 9.2, rank 1. Then minus 3.7, rank 2. Then 2.3, rank 3. Then 11.9, rank 4. Then 14.9, rank 5. Then 19.6, rank 6. Then 20.3, rank 7. Then 22.6, rank 8. Then 27.0, rank 9. And then 27.7, rank 10. So I have just switched to the ordinal scale. So now instead of percentage I have ranks, and I can do the same. I can do what we did in previous example. I can find sample Spearman's coefficient, so I can find sum of square differences of the rings first, and then the sample Spearman's rho, and so on. So the number of observations is very low here, so we have only 10 observations. So let us split the range, divide the range into two intervals for the first variable and for the second one. So for the first one, is the minimal value is minus 1.6 and the maximal is 5.6. Let us say that the intervals are from minus 2 to plus 2 and from plus 2 to 6. And here the minimal is minus 9.2 and the maximal is 27.7. So let us say that the first interval is from minus 10 to plus 10, and the second interval is from plus 10 to 30. So if the number of observations, if the sample size were greater, then we would divide into, not into two intervals, but maybe into 3 or 4 intervals. But our sample size does not allow us to make number of intervals more than 2 in this case. So, and after this we can fill the contingency table. So we can say that we have from minus 2 to plus 2, from 2 to 6 here, and here we have from minus 10 to plus 10 and from plus 10 to 30. And so now let us see. So 1.5, 14.9. This observation is here in this cell. 0.2 minus 9.2. So it is here. Minus 0.1. 19.6 here, 2.8 2.8, 20.3 here. Then 2.2 minus 3.6 here. Then minus 1.6, 27.7 here. Then minus 1.3, 22.6 here. Then 5.6, 2.3. 5.6, 2.3 here. Then minus 1.4, 11.9 here. Then 1.4, 27. 1.4, 27 here. So we see that here we have one observation, here two, here 1, 2, 3, 4, 5, 6, 6, and here 1. And so these marginal sums are 3, 7, 7, 3. So this is the contingency table. So then we can apply the Pearson's chi-square test or other tests that are special for nominal data. So these were the examples how we can switch from the numerical scale to the ordinal scale and to the nominal scales.